Hello, this is video number 6 on my single variable calculus 2. In this video, we're going to talk about another application of the integral, which is arc length of graph of a function. So let's just start with a function. Let's say y equals f of x, and we want to find the length of this graph of the function from x equals a to x equals b. So how do we approximate the length of this function? Well, this idea is something that you probably have seen before. So how do we approximate the length of a circle? So what we do is we divide this circle into small pieces, and then we look at segments connecting these points, and that would give us some approximation for the circle. So you can do that repeatedly. You can get like a triangle, a square, a pentagon, a hexagon, etc. And then you get better and better approximations for the circumference of a circle. So we can do the same thing here. So we can divide this into smaller pieces and then add these up, and that gives us approximation for the circle. So we're going to start with dividing the interval a b into sub-intervals. So let's say x0, x1, all the way to xn, and then we pick these points. So these points are, the first one is x0, f of x0. The next one is x1, f of x1. We find the distance between x1, f of x1 and x0, f of x0. So the length of ith segment, which would be connecting x I minus 1, f of I minus 1, f of xi minus 1, and xi, f of xi. This is square root of the difference of the x coordinates, xi minus 1 squared, plus the difference of the y coordinates, f of xi minus f of xi minus 1 squared. Now, one thing that we need for this one is the mean value theorem. So the mean value theorem is something from Calc 1 that it tells us that if you look at a function f from a, b to r, there is a point in between a and b that f prime of c is equal to f of b minus f of a over b minus a. In other words, if you look at the graph of this function, the average rate of change, which is the slope of the secant line, is the same as the tangent line somewhere in the middle, somewhere in between a and b. So there's a c that f prime of c is f of a minus f of b over a minus b, or f of b minus f of a over b minus a. Now if you multiply this one by b minus a, we get f prime of c is equal to, or rather times b minus a, is equal to f of b minus f of a. So we're going to use this one in this problem. And if we do, we get f of xi minus f of xi minus 1 is equal to f prime of, let's call that ci, times xi minus xi minus 1. Now this is what we called delta xi. So this is f prime of ci delta xi. If we take that and plug it into that formula, the distance formula that we had, we're going to get square root of delta xi squared plus f prime of ci delta xi squared. Now we can factor delta xi squared. If we factor this delta xi squared, we are going to get 1 plus f prime of ci all squared. And then because of this square root, we're going to get delta xi outside here. So this is the length of the ith segment. So the arc length of C is approximately the sum of these quantities, 1 plus f prime of ci squared delta xi, I equals 1 to n, which is a Riemann sum. Therefore, as delta xi approaches 0, this Riemann sum approaches the integral from a to b. The integrand is this function, and this turns into dx. So that gives us square root of 1 plus f prime of x squared. So in the ith interval, we have the sample point of ci, and then dx. So this is the length of the arc c from a to b. Okay, so for the rest of the time, we're going to do some examples on this. So the first example is find the length of each of these curves. The first one is natural log of x over 2 minus x squared over 4. So what is the arc length? It is the integral from 1 to 2. They gave us the limit, square root of 1 plus derivative of that squared. So derivative of natural log is 1 over x, and there's a 2 at the bottom, so we get 1 over 2x minus derivative of x squared is 2x over 4, and that is squared. So we're going to get 1 to 2 square root of 1 plus 1 over 4x squared minus, so this simplifies to 2 here. We can do 2 times 1 over 2x times x over 2. That's the 2ab term. And then plus x squared over 4, and then dx. So note that all of that is under the square root. So we're going to have to simplify this. This is integral from 1 to 2 square root of. Okay, so let's see what this is. We have a 2 here that simplifies with that. X simplifies with that. So this guy becomes negative 1/2. I have a 1 here, so 1 minus 1/2 is 1/2 plus 1 over 4x squared plus x squared over 4 dx. Now we're going to take the common denominator. So 4x squared, 2x squared plus 1 plus x to the 4th. All of that is integrated dx. Okay, so if you look at this one, you see that there's a perfect square on top. So this is x squared plus 1 squared over, and at the bottom, it's also a perfect square. So this is the integral from 1 to 2. Square root of x plus x squared plus 1 squared is x squared plus 1. And at the bottom, we get 2x. Now notice that x is positive because the limits of x are between 1 and 2. Therefore, so x is positive. Therefore, square root of x squared is x rather than negative x. Now we're going to have to integrate this. Integrating this requires you to split this into two different integrals. We get 1 over 2x, and then each one of these can be integrated. So the first one is x squared over 4, and the next one is 1/2 natural log of x, and it's from 1 to 2. So plug in the values. We get 4 over 4 plus 1/2 natural log of 2 minus 1 over 4 minus 1/2 natural log of 1. Well, this one is 0. 4 over 4 minus 1 over 4, that's 3/4. And then plus 1/2 natural log of 2. So that is the answer to the problem. Now the second part is another question about finding the arc length. So what we're going to have to do, we're going to have to use the same formula. So here is the second part. So it's integral. Limits of integration were given as 1 to 3, and the function is 2x to the power of 3 halves. So it is 1 to 3 square root of 1 plus 2 3 halves x to the power of 1/2, and then we're going to have to square that dx. This is integral from 1 to 3 square root of, the 2's cancel, 3 squared is 9, x to the 1/2 squared is x dx. So next we're going to have to do the integration. This requires u substitution. So we can do u equals 1 plus 9x. Du becomes 9 dx. So dx is 1/9 du. Limits of integration become, well, if x is 1, u becomes 10. If x is 3, u becomes 28. 1 plus 9 times 3. So this becomes integral from 10 to 28 root u du. And we have to divide that by 9 because dx is 1/9 du. So we have 1/9, and then we can integrate u to the power of 1/2. That would be 2/3 u to the power of 3/2. If you differentiate that, you get 2/3 times 3/2 u to the power of 1/2. And this is from 10 to 28. And finally, we'll have to plug in the values. So we get 2 over 27, 28 to the power of 3/2 minus 10 to the power of 3/2. So this is the answer to the problem. So let's do one more example. Find the length of the curve given by this. So let's start doing the same formula. So we have integral from 1 to 2, square root of 1 plus the derivative of this whole thing. So the derivative of integral from 1 to x root 16t to the 6 minus 1 dt, all of that squared dx. Now, one thing that you need to remember for to be able to solve this problem is that derivative of integral is the integrand. So that's integral from 1 to 2 square root of 1 plus. When you differentiate an integral, you get the integrand, which is root 16x to the 6 minus 1. And then there was a square here. So dx. This is integral from 1 to 2 square root of 1 plus 16x to the 6 minus 1 dx, which is integral from 1 to 2, 4x cubed dx. And again, here x is positive. Because of that, I can say square root of x to the 6 is x cubed. Otherwise, it would be negative x cubed. And this is x to the 4th, integral of that from 1 to 2. So this would be 16 minus 1. So the answer to this one is 15. So we'll do one last problem and then we will summarize. Set up an integral for the arc length of the ellipse given by this. Do not evaluate. Okay, so this one, they didn't ask us to evaluate. So if you look at the curve, you see that this is not a function. So we can't really use the formula unless it is a function. So what we can do though is, so we know that the intercepts here are 1/2, negative 1/2, and on this side the intercepts are 1. What we can do is we can say, well, the top part is the graph of a function. So the top part is y equals square root of 1 minus x squared over 4. So that is the top part. So we can use the formula for the top part and then double that. So let's first take the derivative of this, derivative of root 1 minus x squared over 4, because eventually I need to be able to differentiate this and put it into the formula. Okay, so derivative of that would be, first we have to do 1/2, then 1 minus x squared over 4 to the negative 1/2. And then derivative of inside. Derivative of inside is negative 2x over 4. So that's the derivative of inside. Now we'll have to square that. So if we take the derivative of square root of 1 minus x squared over 4 and then square that, we would get, well, this one is 1/2. So we would get 1/2 here, 1/2 here. So we get 1/4 x squared 1 minus x squared over 4. And then we're raising this to the power of 2. So we get to the power of negative 2. So this would become x squared over, we have a 4 here, and this one would be 4 over 1 minus x squared. So this would become x squared over 1 minus x squared. So that's the derivative squared. So the arc length becomes twice the integral that I'm about to write. So the limits of integration for x are from -1 to 1, because we know that the graph goes from -1 to 1, and we have to double that because it is the whole ellipse. And then we have square root of 1 plus, we did all the computation here, so that's x squared over 1 minus x squared dx. And simplifying that gives us the square root of, if you take the common denominator, we get 1 over 1 minus x squared dx. And that is the answer to the problem. And they asked us to not simplify, so we don't really need to simplify that anymore. So just again to recap, what we did was we broke it down into two pieces. One, the top part, which is the function of x, because we can write down the top part as y equals 1 minus x squared over 4, and all of that we have to take the square root. We take the derivative of that, so we get 1/2 1 minus x squared over 4 to the power of -1/2, and then derivative of inside, which is -2x over 4. Simplify, take this and then square that, we get x squared over 4, and then we have to square that, so that means you have to flip this, we get x squared over 1 minus x squared. Then we plug it into the formula, but this is something we cannot integrate. In any case, that would be the answer. So I do have a 2 in front that I forgot. So that's the answer to the problem. So to summarize, what we did was to evaluate the arc length of a graph of a function, then we have to use the formula in integral from a to b of square root of 1 plus f prime of x squared dx. And from Calc 1, remember that derivative of integral becomes integrand. Note that the lower limit must be a constant, and the upper limit must be x. It can't be anything else. If it is something else, then you'll have to use the chain rule. And that brings me to the end of this video. So I will see you in the next video.